Good afternoon, everyone. This is Scott Dahman of PowerWorld Corporation, and I'd like to welcome you to, I think, what is our fifth installment of our user group webinars that we've been conducting around the introduction of PowerWorld Simulator 24. And I'm joined again by Professor Tom Overbye of the Texas A&M University in the Department of Electrical and Computer Engineering there. He is a PowerWorld Corporation co-founder and the author of the original software that became PowerWorld Simulator. He was previously a professor at the University of Illinois at Urbana-Champaign. We are located in Champaign, Illinois. Professor Overbye received his bachelor's, master's, and PhD degrees from the University of Wisconsin at Madison, and after his bachelor's degree and throughout his graduate studies, he was employed at Madison Gas and Electric Company. He's been very involved in specific aspects of PowerWorld Simulator, ever since the founding. And this is one of the things that he's involved in is the geomagnetic induced current functionality in PowerWorld Simulator. And this is a new tool that integrates that tool and simulator with EPRI's, the Electric Power Research Institute harmonic calculator called GICHarm. So with that, I'll let Tom show what we have now.
Okay, thanks, Scott. The goal of this presentation is to show you it's kind of hands-on. I mean, not that you'll be doing hands-on, but it's sort of like showing you how to actually use the functionality. What we've got is over the last couple of years, PowerWorld has been working on integrating in EPRI's GICHarm program. The GICHarm program is used to do harmonic analysis associated with geomagnetically induced currents, what we affectionately call as GICs. I've been working in the GIC area for probably close to 15 years now. And over that time, we have gradually added more and more functionality to PowerWorld. So PowerWorld, particularly simulator, is now pretty good at doing analysis of electric grid impacts from geomagnetic disturbances, what we call GMDs, and also from what we call HEMPs, high altitude electromagnetic pulses. But both of these can cause significant harmonics. These harmonics can then impact power system devices. For example, they can trip capacitors. And during GIC events, usually you have voltage concerns. So you really want your capacitors and you really would like them to not trip. So this is a new tool that helps you do this analysis. I should say, part of the reason for the recent work in this is funding that we received from the U.S. Department of Energy. PowerWorld didn't get funding, Texas A&M got funding. So this has been a project that is joint between several of the national labs, including the Pacific Northwest National Lab, EPRI, and Texas A&M. But associated with that, PowerWorld has been kind of paying attention to what's going on and also modifying their code to better support this analysis. Okay, so if you're familiar with geomagnetic GMD analysis, NERC put out a black diagram probably 10 years ago now that shows the different things that you have to do GMD analysis, and that black diagram is still completely accurate, and actually a lot of progress has been made on that. I know there's good tools for doing transformer modeling or thermal modeling. EPRI's got a nice tool associated with that, and they also have a nice tool associated with what we call the B to E conversion. What we're going to talk about today is in addition to this tool, it sort of falls into the assessment criteria to look and say, okay, if the GICs cause harmonics, are those harmonics going to trip devices? And if they trip devices, then we need to take that into account and redo our GIC analysis, including potential outages from the harmonics. So if you're used to doing GMD analysis or more broadly GIC analysis in PowerWorld, you know that we have what we call the GIC analysis form. The GIC analysis form lets you study either the impact of a constant, or well, yeah, it's really a constant electric field on the grid, what we call single snapshot analysis, or time varying electric fields on the grid, and or spatially varying electric fields on the grid. So we can handle all of them. This is a single snapshot page. This shows the time varying electric field input analysis page where you say, okay, the electric field that is being superimposed on the electric grid is changing both with time and spatially. What impact does that have on the GICs? And this tool lets you analyze that. Not really going to focus on this tool per se today. What I'm going to focus on is the additions we are making for harmonic analysis. Okay, so in adding harmonic analysis to the GIC calculations, if you did the traditional standard power flow approach, what you would do is using an assumed electric field, you'd calculate the geomagnetically induced currents. And these are they're quasi DC, so the analysis is fairly straightforward. It's essentially solving a DC circuit. And then we look at the positive sequence impacts of those currents and we represent them in the power flow, then we solve the power flow. And primarily this involves getting increased reactive power loading on your transformers. When we want to add harmonics, what we're going to optionally do is again calculate the field, again calculate the power flow, then we're going to calculate the harmonics to see what impact they have. And in particular, we're going to look at something called total harmonic distortion in the voltages, which I'll talk about a little bit later on. Then we'll determine if that is so high that it would likely result in devices tripping, for example, capacitors. If so, we take the affected devices out of service and then redo the analysis. So that's the presentation in a nutshell. So now I'm going to get into more of the details on doing this. Okay, so new in version 24, and actually it just came out in, or it is coming out in a recent patch, like a patch that's available in a couple days. There's a page on the GIC analysis form that's called harmonic analysis. If you go if you go down here, you'll see harmonic analysis, and that brings up this page that has functionality that lets us do harmonic analysis. All of this requires the use of an external program, and that external program is GICHarm, and I'll talk about how you get GICHarm in just a little bit. But before I do that, I did want to go through a little bit of background on harmonics. Some people are very familiar with harmonics. Other people are not particularly familiar with harmonics. Last semester, I taught our power system analysis class here at A&M, and I did say the word harmonics, but usually when we teach power system analysis, we don't do too much on harmonics. Of course, in an electric grid, if it's operating at 50 or 60 hertz, that's the primary frequency. And then integer multiples of the primary frequency are known as harmonics. And harmonics have always been present in grids. There's papers that, if you go back to the 1920s, that are talking about harmonic impacts on the grids. But one of the changes is as we add more power electronic devices into the grid, they induce more harmonics, and that is causing potential for increasing problems. Geomagnetic disturbances also can cause harmonics by going through by causing transformer saturation, which is our focus here. If you're looking for additional information on this, these are two sources. There are several books on it. I haven't really read those books, so I can't vouch for any of the books. But if you're looking for books on harmonics, oftentimes they'll be associated with a book on power quality. If you'd like a quick overview, our Texas colleague Matt Grady, who was with Baylor University, he has put out a nice document in 2012 that I have often referred to when I'm dealing with harmonics, and that's freely available. And I've given the link there, and I'll be referencing it in this presentation. EPRI's also put out a nice document that talks about harmonic assessment, particularly associated with geomagnetic disturbances. That's also freely available. I've given you the link there, and I'll be mentioning that in the presentation as well. With respect to harmonics, if you want to figure out how many harmonics you have, if you've got a periodic waveform, Fourier series analysis says that any periodic waveform can be represented by a DC value, a fundamental frequency, and then integer multiples of that fundamental frequency. And those integer multiples are known as the harmonics. If your system or if your signal has half wave symmetry, so one half kind of looks like the opposite of the other half, which is very common in power systems, then you will only get odd harmonics. So you get a first, the fundamental, then you get a third harmonic, a fifth harmonic. When we talk about geomagnetic disturbances, they actually are caused by transformer saturation, so they don't have half-wave symmetry, so they can induce even harmonics as well. One of the terms that comes up when you talk about harmonics is total harmonic distortion, THD. I'll be using that a lot in the presentation. THD is just a measure of how much harmonic you have, how much harmonics you have relative to your fundamental. So you're just taking a sum of the frequencies above the fundamental, squaring it, taking the square root, and then dividing, kind of normalizing it by the fundamental. And that's the equation there. The THD can be calculated for currents, and if it's being calculated for currents, there's a subscript I there, or for voltages, you'll see a subscript V, and we'll be talking about THDV a lot here. Obviously, if there's no harmonics, then the equation indicates that the THD is going to be equal to 0. Okay, when you analyze harmonics, you if you have a balanced system, then actually you will tend to have harmonics that follow the phase sequence. So if you have a balanced system in your fundamental, you'd have a positive sequence network. Because of the second harmonic is at twice the first harmonic, it's actually going to look like a negative sequence. So it'll affect the negative sequence. The third harmonic, because you've got in a balanced three-phase system, you got a 120-degree phase shift between the phases. At the third harmonic, that looks like 120 times 3, which looks like 360, which means all three of them are in phase. So that means you're going to be dealing with a 0 sequence. Fourth harmonic, positive, fifth, negative. So when we do this analysis, we are going to, of course, need the 0 sequence and the negative sequence values. Okay, this is a slide that I've been showing for about 14 years now. I was actually out at a JSON presentation. JSON is a group that looks into, it's a group primarily of university researchers that looks into issues of interest to the military. They were doing a focus group in summer of 2011 on the electric grid, and one of the areas was on geomagnetically induced, or on the GMDs and the HMPs. So I was out at a meeting there, and Craig Stigmeyer and Ed Schweitzer were also there, so I picked up these slides from them. The slide on the top says, how does a GIC, which is essentially a DC current, how does that induce harmonics? What happens is the DC current superimposes on the AC current, so that means it shifts the AC current. And as the AC current is shifted, what happens is with the magnetic curve as you're going through the IH curve or IB curve there, what you're doing is you're pushing for part of the cycle, you're pushing your system into saturation. When you saturate the system, it's going to cause a distortion in the currents there. And when you get a distortion in the currents, then you're getting harmonics induced. And the image on the bottom there shows the harmonics that can be induced because of GICs. So you can get of course, you'll have the fundamental, but then you can also get a second, third, fourth, fifth, sixth, and higher order harmonics. So when we analyze this in a power flow, we look at the positive sequence impact of these harmonics, and we represent it by increased reactive power loading on the transformer. But sometimes you need to actually consider the harmonics, and that's the focus here. Both the document from McGrady from 2012 and the one from EPRI in 2019 give a nice description of the impacts that harmonics can have on the electric grid. McGrady's one is more general, so he talks about different things there, resonance, tripping a sensitive load, etc. And then in the EPRI document, they focus more on GMDs. And with GMDs, you get impacts on transformers, shunt capacitors, pretty much everything listed there. But the document notes, although capacitors are reasonably robust to harmonics, the tendency for capacitors to amplify harmonic currents and voltages combined with the relatively short thermal time constants make capacitors arguably the most vulnerable to GMD of the major power system components. So our initial focus here is going to be saying what do the harmonics do to the capacitors, with the idea that this could be expanded to consider other devices as well. Okay, resonance is something that comes into play here. If you're an electrical engineer, you probably remember an undergrad experiment where you looked at a LC circuit, and as you change the frequency, suddenly you got a spike in the voltages in the system, and that's due to resonance. And resonance is something that will amplify the voltages and currents at a particular frequency. Now, we design the electric grid so that it does not show resonance at the fundamental frequency, but it does have the potential to have resonance at some of the harmonic frequencies there. So the equations there on the left are some that I got from McGrady's document. So if you want to know how the values of X capacitor and X system impact to cause the resonance, it's given there. Okay. With the electric grid, we had a storm in May of 2014. Some people call it the Gannon storm, and it caused GICs on the grid, and actually it caused GICs that were higher than 100 amps. There's a nice NERC document. NERC had a workshop in October of last year that focused on this event. So if you want more details, I've given you the link there to the workshop material. The top one shows the electric field that was seen during the disturbance. The top left, the top right shows how much GIC currents we had flowing, and in some locations it was over 100 amps of GICs. And this was a relative. I mean, it was certainly it was a bigger, of course, more GICs than we usually get, but it was not by any means a severe storm. The one on the bottom left is a data from PGM that shows a change in their 500 kV voltages. And then the one on the right is a change in the voltages at PJM, and they note that they had a SVC trip during this event as well. There was also recordings that picked up the harmonics. There's a group called Whisker's Lab. They have something called the Whisker Labs tin sensor network. And the Whisker Labs network it models and it measures in real time harmonics that are present on the grid. So they put out a little document that explained how the total harmonic distortion varied on the grid during this event. And as you can see from the graph on the top, which goes through several days there were times where they were seeing some relatively high total harmonic distortion. And the images on the bottom left and the bottom right show how this total harmonic distortion moved around the grid as the storm moved around. So the harmonics, I think a lot of us saw these harmonics as being perhaps higher than we would have expected. So it certainly gives good impetus for the work that we're talking about here. Okay. If you want to do harmonic analysis with PowerWorld, you have to get GICHarm. The good thing about GICHarm is that it is open source, and Bob Arrett's on the phone here, and Bob can mention at the end the specifics on getting it because we were just talking on a phone call, I guess it was just yesterday, about how people can get it. But if you go out to that website there's a couple email addresses to get it, but you can get it. GICHarm runs on top. It's a Windows program. It runs on top of OpenDSS. And if you get GICHarm, what I would suggest is just install the OpenDSS version that comes with the GICHarm download. I've got it installed on my computer here and on my laptop, and I will say my feeling on GICHarm is it's a pretty easy program to install, and it's a pretty easy program to use. Okay, so in doing GIC harmonic analysis, this is what we're going to do. And what I'm going to walk through in the slides is both how to do it separately from simulator and then how to do it within simulator. And being able to do it separately helps give you some confidence in what simulator is doing with the new capability. So the idea here to do this analysis is you solve a power flow with the GICs in it, and you can calculate the GICs. You save the power flow model in the OpenDSS format. You use GICHarm to solve for the harmonics. You load the harmonic information back into the power flow. And if the harmonics are below trip values for your devices, then you're done. Otherwise, you trip the affected devices and go back to 1. PowerWorld, again, simplifies this process greatly by making it all into a single automated process. But I did want to walk through what goes on separately and then manual in PowerWorld, and then we'll finish up automatically in PowerWorld. So in these examples, I am using a 200 bus case. The 200 bus case is a synthetic grid, which means it's a fictional grid, so it can be freely shared. The grid I have is from the grids that we have on the Texas A&M website there, electricgrids.engr.tamu.edu. It's actually one of the earlier synthetic grids that we made. We made it when I was still at University of Illinois, so we modeled central Illinois. It's just a test system that you can use. The nice thing about these test systems that we have on our website is they do have GMD values associated with them. So they've got like substation grounding and things like that. Okay, so if you got this case and you wanted to do GIC analysis with GICHarm separately, what you would do, and you had PowerWorld, is you would load the case into PowerWorld and save it as a raw file. And what I've been doing is using version 33. I don't know if other versions are supported by GICHarm, but I use version 33. And then I save a GIC file using the version 4 format. GIC files now have a version 5 format that PowerWorld supports, but use version 4 if you're importing it into GICHarm. Okay, so after loading the case, this is just walking through how to do the analysis in PowerWorld. Go to the GIC analysis form in PowerWorld, and this does require that you have the GMD add-on for PowerWorld. But you go to the GMD, the GIC analysis form, set it to single snapshot, set the maximum electric field to 1.14 volts per mile with a 45-degree angle. This is just a test storm that I've been using. What this gives you is it gives you 0.5 volts per kilometer in both north and east directions. So then save the raw file and use the form to save the GIC file. To save the GIC file, just go down to the supplemental file options and you'll see an option to save the GIC data in version 4. Okay, so then go ahead and start up GICHarm. And when you start up GICHarm, what you need to do is you need to create a set of OpenDSS format files. So GICHarm has a tool to do this. Just select Tools, PSSE to OpenDSS Converter. You load the raw file. It'll say, hey, give me the raw file. Then you load the GIC file. If you have sequence data, you can load a sequence file as well. If you don't have sequence data, and this is what I have been using in the testing I've been doing, there are default scaling values that are used to figure out what the negative and zero sequence values are. So if you don't have it, it's okay, just use the defaults. And then it will let you save the you just click GIC harmonics tool and it saves OpenDSS format files. If you're used to PowerWorld, PowerWorld will save a case in one file, a single PWB file. OpenDSS and GICHarm save it in a whole bunch of files. So you'll get a whole bunch of DSS files. One might have the commands in it, one has transmission lines, one has loads in it, and there's a master file. The master file controls it all. So you'll get this set of files. Okay, then while you're still in GICHarm, all you have to do is select File, Open, and then you select the save master file that you just exported, which loads all the other files. Then you select Load OpenDSS Circuit right here. Once you do that, if you want to use the tool's internal GIC calculation, which is what I've been doing for testing, is just click then internal GIC analysis, and it will take the assumed electric field in the OpenDSS format, which is by default 0.5 volts per kilometer in the east and north directions. It will use that. Otherwise, you can import GIC results as in a CSV format. And ultimately, this is something that we'll be using in the PowerWorld implementation. But then just click set the number of iterations that you want to run. And I have been using 1 for testing, but I think the default is 5. But if you just want to get a feel for what's going on, just set it to 1. Then select Run Iterations, and when you do that, it will crank up and run on your computer. The first time I ran the 2000 bus case on my computer made noises I didn't think it could make. Because GICHarm uses a parallel processing, so it gets good use out of your computer. So all these fans turned on and it did the iterations. The 2000 or the 200 bus case, I just was running it for making up these slides. I found it took about 14 seconds to run on my computer. So once you do that, then you just go to Tools, Export Tool, then select the THD monitored bus bars and available bus bars, the tools right here. Select the THD monitored bus bars. That's what I've been doing because I've just been focusing on the total harmonic distortion, available bus bars. Usually I just select them all and then you select selected element and it gives you a directory to save the results in. It'll save a CSV file with the file name THDV __ available _ bus bars, a CSV file, and that's the format of the file. Okay, so then you've got a file that's got total harmonic distortion in it. Prior to the work we did in PowerWorld, you couldn't really do anything with that file, but now we've modified Simulator to be able to store these bus total harmonic distortion values, and you can actually directly load that file into Simulator. So on this GIC analysis form on the harmonics tab, you just click import selected GICHarm results, and that will load up your file. When you select this, it'll give you a directory to load them in. This gives you the results here. Once these are loaded, they just become other regular PowerWorld simulator fields. So if you go to the bus display, the standard bus case information display, there's an option now in the available fields called harmonics, and it will let you see in this display the total harmonic distortion on each one of the phases and the total values. And this will be saved with your simulator case. So if you save a simulator case, this will be saved with it. Yeah. Now, GICHarm does not calculate the total harmonic distortion at every bus. It just calculates them at, I think, the switch shunt buses and the transformer buses. Okay, so with this information in Simulator, you can visualize it and use it and export it as an aux file and do all the stuff that you would do with Simulator data. For example, here's a geographic data view display when I did the Texas 2000 bus case and I looked at the total harmonic distortion on that, and I can visualize it just like I visualize any other thing in any other field in Simulator. Okay. So then the next step is to use these values to do something. What we would like to do is we would like to open up the capacitors that have THDV values above a threshold. Now, this could be done manually. You could load it into a case and then you could look at your switch shunts and decide if the value is too high, you open up that device, but that would get rather tedious. So, and it also couldn't be automated. So the solution to this is to use something that we call the PowerWorld PFW models. So to give you a little background on those, over the last few years, PowerWorld has been working a lot on modeling the weather impacts on the electric grid. Oh, I was talking about the PFW models, and we use those in the harmonic analysis. We've used them in the past and currently use them a lot for weather analysis. For example, here's a PFW model for a wind power curve. We have a project that we hope will be starting very soon with Department of Energy that we're going to be looking at other applications of PFW models, including on things like earthquake risk. But we are using them here to set up models for the impact of the total harmonic distortion on the devices, the capacitors. So adding PFW models is extremely simple. Going back to the going back to the GIC display, the harmonics page. If you look at the OpenDSS switch shunts page, there's a if you just right click there, you will get a local menu, and then in that local menu, just select insert new PFW models, and it will then give you the option to insert uh, models that relate GICs, or the not the total harmonic distortion for the switch shunts. Currently, there's just one. We call it the total harmonic distortion voltage simple model. That model just says, okay, for a total harmonic distortion at the switch shunt of this value, let's say 3%, issue a warning, and if it's above 5%, trip the device. Okay, so you put these in and you can customize these as much as you want. By using the PFW model approach, we can descend new types of devices very easily. So if you want a more complicated representation, that will be possible as well. Okay, so I've gone through the process separately. What we've then done is in simulator is to make it much easier to do this by integrating it into simulator. And we give you two choices for doing this. You can either run it manually within simulator or automatically. Manually is a good place to start to make sure that you kind of understand what's going on, and then as it gets more useful in practice, you'll be able to automate it. And eventually, we're probably going to create script commands that let this be done. But it's still certainly a research area to say, okay, how do we use this harmonic analysis with practically sized power systems? So when you go through this analysis in PowerWorld, these are the steps that you go through, and I've got that on the next slide here, so I'll just talk about it here. If you wanted to do the manual process, once you load a case up, you will click on initial error check. That just makes sure that things are set up for GIC analysis. You solve the power flow with GIC values, so you'd click that button. You would then click a button to save the case in OpenDSS format. It's a simple click of a button, but a lot goes on in taking the PowerWorld model and saving it in OpenDSS format. With this button, what we're trying to do to some extent is to duplicate what GICHarm does with their export from a raw file into the OpenDSS format. So we're eliminating that step. The advantage in doing that is once it's directly in simulator, you don't have to go through a raw file. And there's also the potential to greatly expand the functionality. So that you click that button, then manually run GICHarm. Click that button and it will run GICHarm in a batch mode. I'll talk about that in a second. Then you export the selected GICHarm results. Or I'm sorry, when you run GICHarm, it'll save the results automatically. Then you import them into simulator. You apply the PFW models, and it'll store an iteration so you can keep track of the iteration. If nothing changes, you're done. If something changes, then you go back and do this manual process again. So this is the, I guess, a slide on writing the simulator data in the OpenDSS format. I will say that I am not by any means an OpenDSS expert. Maybe the opposite of an expert. But in developing this code, what I did is I looked at what GICHarm was doing in terms of producing a file, and then I got simulator to mimic that. So let me. I'm just setting up the case here. That's not, it's not letting me show you the PowerWorld one. It's just on the PowerPoint, but yeah, so this produces the output. It writes a whole bunch of files, OpenDSS files. It'll actually currently it produces 24 of them. When you load OpenDSS files into GICHarm, you select the master file. Since this is something that PowerWorld is exporting, we can also show the data that it's exporting in one of our case information displays, which is what we do. So on the bottom here, if you want to see all the data that's written into the OpenDSS format files, it's shown there. For the 200 bus case, this file has about 2,700 lines in it. So we're just mimicking what GICHarm is doing currently, and that helps us on validation, because what I've been doing for validation is doing the external process where I save it in GICHarm, and then I check and calculate the harmonics. Then I save it in PowerWorld, and I use GICHarm, and I check the harmonics and see if they're the same. If they're not the same, I know there's something associated with the export that is incorrect. So then I go and track it down. The way we run GICHarm in PowerWorld is GICHarm has something that they call the batch analysis tool. It's the file GICHarm under GIC_harm_cmd_exe. PowerWorld just runs that file as an external process. And this is similar to what we do in simulator. Like in simulator, if you want to open a PowerPoint document, you can open a PowerPoint document because we just run the associated code for that. Or you can open up a map, in like Google Maps and see that. We're doing the same thing. We just run that external process, which is shown on the top line here. And then GICHarm has, you just set extra parameters, and I showed the extra parameters that are there. Then you click run process, and the dialog sticks around until it's done. If you want, you can automatically close the dialog when it's done. Okay. So there's several options here, and you'll see some of the options. There's actually more options available that we just have not yet set up displays for, but that's all coming. Then I'm not going to show it here, but the alternative to doing this manual process is to just click the run automated analysis with GICHarm. And what it will do is it will run through this process up to a specified number of iterations. And the way the iterations end is if there are no new devices that are switched out. So hopefully you don't have high enough harmonics so nothing switches out. So you go through one iteration, but if not, it will automatically do this for you and continue until either it hits a maximum iteration or the power flow does not solve. Which, with GMDs, that certainly is something that could occur. Okay, so summary, this is integrated into simulator. I would put it in the stage of being beta functionality. It certainly progressed quite a bit over the last several months. I wouldn't say use this for operational studies quite yet, but it's getting very close to being used for that. I've been testing it on the 2000 bus synthetic grid, and the next step is to test it on larger grids like the WCC. I should say that GICHarm and PowerWorld provide the option to only export a portion of the grid, and that's most likely what you would want to do. Because if you're doing harmonic analysis, you probably don't want to do a whole interconnect. So if you do a portion that you're concerned about, that will save on computation. But as when we discuss this with people on the project, the comment is always like, this is much faster than doing a full EMT simulation, and we're getting a lot of the benefits in doing that. So there's still more work to be done, but I think we're pretty close, and it's certainly at the stage where people can start playing around with it. And we really kind of like to know how people would like to use it. And there certainly is a need for more research, and we are continuing doing research in this area. So I'll finish up there, and hopefully there'll be a few questions. And I should say that that picture there is Kate Davis, who is one of my faculty members, and Kate and her husband Matt just had a new baby boy born on the 4th of July. So we're all excited for Kate and Matt.
Tom, this is Scott. What's understood about the switch shunt models, the PFW models? Are those parameters fairly standard, or is there a need to like customize them on a device by device basis because maybe different capacitors have different response to the harmonic?
Well, luckily we got the expert on the phone call, Bob Arrett. I asked Bob what I should set for default value, and he said 5%. But certainly it's a model, and people can set the values to whatever they want. So,
is there a time component? Like, can you run this through transient stability, like you might with a EMP simulation, or is it pretty much designed just to look at the steady state that you get out of the power flow?
well, currently you can't run it through stability. No, currently it takes a power flow output. So I have been thinking about that for HEMP studies where you might look at a snapshot in time, say, at this point in time we have these GICs. What would our harmonic load be at that point in time? So it'd be more of a snapshot analysis to give you a feel. The takeaway on doing this harmonic analysis is that it does take time to do. And one issue, which is probably a research issue, is to say, okay, if we have a big grid, like let's say we wanted to do all of ERCOT, well, harmonics don't flow that far. So, if you're looking at the fifth harmonic, the impedance of the grid gets to be pretty high at the fifth harmonic, so it's not like they're going to flow very far. So maybe you can analyze the grid separately. Look at one area, then look at another area, then look at another area to save on computation. Or, if you're a particular utility, you might just be interested in your area. And the GICHarm tool and PowerWorld now has the option where you sort of specify what areas in the grid you're interested in. You can start playing around with us and giving us feedback on what works and what doesn't work. The manual process that I went through, or the separate process that I went through, it's like you can go get the GICHarm tool today and do that analysis, and that's all set to go. And then PowerWorld will load up that CSV file that has the total harmonic distortion in it. So you can use the existing export capabilities of GICHarm today.
All right, thanks, Tom. And I don't see any questions in the chat. And if nobody has anything at this point, we will conclude. And just thank you for joining us.
Yeah, and please, if you have any questions or comments, send me an email. Bob, did you want to say something?
Yeah. So first off, thank you, Tom. It was a great job. Born on the 4th of July. I think that was a movie or something, wasn't it? But I do want to say to Scott's question about the time component. This was all geared to addressing the TPL 7 standard. So those peaks last for minutes. So it's really not a time component as far as a time delay on those harmonics. So and again, that's part of the speed of the computational time of being interested in the peak. I will say you can download this on EPRI.com. If you're not a member, you just have to agree to just a license agreement. I'm not a lawyer, but basically just says that you won't hold EPRI accountable if you get the wrong answer. Um, but you should be able to get that. If you have any issues, just let me know, and we can go from there. And the GICHarm support, that would come from EPRI. If you have any questions on that, and of course the integration in PowerWorld, um, yeah, PowerWorld would field those questions. But again, thank you, Tom.
Yeah, I'm pretty. I think there's a lot of potential here.
All right. Thanks, Tom. Thank you, Bob. And thanks to everyone who joined.